we can use the idea of impulse, that idea of impulse being the change of momentum, and also being equal to the average force applied times the time that it's applied for, to work out the force of a fielder catching a cricket ball. What force does the fielder apply to the cricket ball? So here we've got a cricket ball which starts off flying through the air at 20 meters per second, and it has a mass of 0.16 kilograms. Now the time of impact of the ball on the fielder's hand is 0.1 seconds, which it could be, and we need to calculate the average force applied by the ball on the fielder's hand. Now that will be the same as the force applied by the fielder on the ball. Remember, Newton's third law says that forces always come in pairs that are equal and in opposite directions. Okay, so let's set up this calculation. So let's do a before and after diagram, which is a useful thing to do for momentum calculations. So here we go. Beforehand, we've got the ball, cricket ball, moving along 20 meters per second. It has a mass of 0.16 kilograms, so m equals that. This is the initial velocity, so we could call that u for initial, which is the usual letter to describe the initial velocity. Well, what about afterwards? Well, afterwards we've got a situation where the ball is now caught. It's not moving with any speed at all, so we could say that our final velocity is 0 meters per second, and it still has a mass of 0.16 kilograms. Good. Sometimes it's good to ask, what can I find out? Well, from this I can find out the change in momentum. So I'm going to abbreviate that with the delta sign, which means change in. So I can just say change in momentum. Now the change in momentum here is going to be the final momentum minus the initial momentum. And the equation is mv, that's the final momentum there, minus the initial momentum. So let's put the numbers into that and see what we get out. So we've got 0.16 kilograms, that's the mass, times by v, which is 0, minus 0.16 times by 20 meters per second. And from that, we will get out minus 3.2 kilogram meters per second. So that's the change in momentum. Okay, well, we need to work out the force that was applied to this ball to slow it down. And so what we had here was a situation where the ball, which was moving, had a force applied to it by the fielder, and that was applied for a time of 0.1 seconds. To bring it to rest, to give it a change of momentum of minus 3.2 kilogram meters per second. So we're trying to find the force in newtons. What else could we find? What else do we know about the change in momentum? Well, it's called impulse. An impulse is equal to the change in momentum. An impulse is also equal to force times by the time the force is applied for. So let's use that number for our change in momentum, and we'll use this part of the equation to help us work out the force, the average force applied by the fielder on the ball, which will be the same as the force applied by the ball on the fielder. Let's put the numbers in now. So we know that minus 3.2 is equal to the average force times by 0.1 seconds. There's our time, 0.1 seconds. So to find the force, we need to divide both sides by 0.1. And we'll find that would equal F equals minus 32 newtons. And that would be the average force applied by the fielder on the ball to bring it to rest. And it will also be the same force that's applied by the ball on the fielder due to Newton's third law. So there's an impulse calculation using the two equations, change in momentum equals mv minus mu, and that impulse, which is the change in momentum, is the average force times by the time that the force is applied for. Hope that makes sense.